Now, let's move to our second example to illustrate further the idea. This time, we're going to consider um, a rational function uh, for which the denominator is consistent with case 2. Okay. Um, yeah, I think this is a nice example here. Evaluate the integral of 1 minus x over x cubed plus x to the fourth. Okay. Again, the first task here is to find the partial fractions corresponding this. Okay. In other words, to express this as the sum of partial fractions. Or that means that we decompose that. No? Again, the case in relation to that is this one, because if you notice, x cubed is common here, and then you have x plus 1. In other words, this can be factored as x cubed times x plus 1, where x cubed is a repeated linear factor, right? Okay. It is repeated thrice because you have x cubed or x times x times x. Okay. So according to this, we can decompose this fraction by following this idea. No? Depending on how many times the linear factor is repeated. Okay. I will show you, I will do the computation myself here because it's not easy to type the solution. So I will do it by hand and observe how we decompose this or express this as sum of partial fraction. Okay. So we have this. I'm going to first express this no as sum of partial fractions. So I will first separate the integrand there. Let's put a line here to separate the computation for the decomposition of the integrand. Okay. Okay, then the next step is to factor x cubed plus x to the fourth, which is x cubed times, I'm sorry, that's times, okay. Then you have 1 plus x, right? Okay. And then we rewrite the numerator. And then after that, take note that x cubed is a repeated linear factor. So we have 1a over x plus b over x squared, right? Then plus c over x cubed, and then plus that one is linear, so we have d over 1 plus x. Okay. Then we combine this as a single fraction. Obviously, the common denominator is the original denominator there, which is x cubed times 1 plus x. And then the numerator, the first numerator will become 8 times x squared, right? X squared times 1 plus x. Then for b, plus b times, this time we have x, no? Times 1 plus x. And then plus c times 1 plus x na lang kasi that's x cubed. And then plus d times x cubed, right? Okay. And then we combine like terms, or first, let's distribute the x squared there. So we can write that as a times x squared plus x cubed, and then plus b times x plus x squared, okay, plus c times 1 plus x plus dx cubed over x cubed plus 1 plus x. Now, notice that the two denominators can be cancelled, so the numerators are equal, no? 1 minus x times a times x squared plus x cubed plus b times x plus x squared, okay, plus c times 1 plus x plus dx cubed. Okay. After that, we combine like terms. So 1 minus x equals dx cubed and ax cubed. So we have a plus d, right? So times x cubed. What else? For x squared naman, we have ax squared and bx squared. So we have a plus b times x squared, and then those terms with x, we have b and c, so b plus c times x, and then the constant term, we only have one, okay, which is c. And when topolonyms are equal, the corresponding coefficients are equal. So we have a plus d equals 0 because there is no term there with x cubed. This time we have term with x squared, that's also 0, no? And then b plus c, we have that corresponds to negative x. We have b plus c equals negative 1. And then the constant term c equals 1. Okay. Oh, we have the value for c, right? We have the value for c. We now solve for b. We substitute that to the equation. So b becomes negative. And then we substitute that b to the second equation. So a minus, so a equals positive. And then next is d becomes negative 2, right? Okay. Okay, so we now have the value for a, b, and c. Okay. We substitute those to our partial fractions, and we can now rewrite the integrand as, okay, a over x, where your a is 2. You have 2 over x plus b over x squared, where your b is negative 2. So you have negative 2 over x squared. And then next is c over x cubed, where your c is 1. So plus 1 over x cubed. Then plus d over 1 plus x, where your d is negative 2. So you have negative 2 over 1 plus x. Okay, then dx. Then we put it into the form where we can easily evaluate the integrand. So we factor out 2, that we have 1 over x dx minus 2 over, now take note, it's better to write that as x to the negative 2, right? So we can use the u to the n du. And then this one also, plus integral of x to the negative 3 dx. And then this one also, which is negative 2 integral of 1 plus x dx. Okay. And now, so this is 2 ln of the absolute value of x This one here is -2. That's u to the NDU, so -1 over -1. Then this one is plus x to the -2, okay, over -2. And the last one, minus 2 times ln, because the du is present. 1 plus x, then plus c. Okay, then we have, it's actually better to combine 2 ln of x and -2 ln of 1 plus x, because they have the same coefficient. They're whole numbers. The coefficients are whole numbers, so we can write that as ln of the absolute value of x over 1 plus x. We can remove the absolute value because this is squared, right? This is squared. And then this one positive because that's 2 and okay, 2 over x. And this one here is minus, it should be 1, okay? 1 in the numerator over 2x squared, then plus c. Okay, so this is our integral. Now, so going back to our solution again, we have the this is decomposition of the rational function, which leads us to the value of a, b, c, and d, and therefore we can write this as sum of these partial fractions. So, and also our solution for this problem is indicated here. Okay. Okay. As for our second